Thank you. Welcome to my talk, and I would like to begin by thanking the organizer for giving me this opportunity to present my work. So this work is something you can find on the archive preprint. It's a thermally driven quantum refrigerator autonomously resets superconducting qubit. And the experiment was done in 22Q lab in Chalmers University of Technology with theoretical support from the group of Nicole Younger-Halpern in Maryland. I'll just say a few words about 22Q Lab because it's a new lab. It's about 3 years old, led by Professor Simone Gasparinetti. And we follow a wide range of research directions using superconducting circuits, going from fundamental research to applied research. So the topic of my talk is in quantum thermodynamics, which forms the fundamental research. But we also go all the way to quantum computing with continuous variable, just like the last speaker, all the way to building hardware in the lab as well. And we're also hiring students and postdocs, so anybody interested to work with us, get in touch with us shortly. So today's topic is in the context of quantum thermodynamics, and in our experiments, one of the things that we have a broad approach in our research is about looking for quantum advantages. So for example, how would you beat any classical machine in terms of power output, charging speed, precision, and so on. But also we are thinking along the directions of having some practical applications, where for example, you could deploy such a quantum thermal machine in a useful setting to do something useful. And one experiment that we have come up with is to use this in qubit reset. So let me tell you what the qubit reset is about. So it's to reset the qubit to a ground state. And this is a very important step in quantum computing, where speed and fidelity are very important metrics. For example, resetting ancillary qubits is quite key to the quantum error corrections. And other passive approaches such as thermalization may be too slow and too unfaithful. So that is why we have to come up with some particular protocols. Some of the very commonly used protocols are called active reset and unconditional reset, where you use feedback or some coherent drives to do this. But this is typically expensive. It becomes more expensive as you try to scale with the number of qubits. And in our research, we were asking, how can we do this job with minimal thermodynamic resources instead of using those expensive resources that is used in quantum computing normally. So here comes the absorption refrigerator. Absorption refrigerators are useful thermal machines that can cool an object, but are driven by heat coming from a hot bath instead of the traditional thermodynamic work. Actually the first absorption refrigerator was patented by Einstein and his student Szilard back in 1930. And now it's actually quite prevalent in macroscopic machines, as macroscopic machines in industry. So for example, these are very good, these do not have a very good coefficient of performance as refrigerators, but they have other good features such as they have very high utility because they can use excess waste heat formed in factories and other places to be used to cool something, to do something useful. Usually they only use thermal baths, which are abundant in nature. And they're also autonomous, which means that there's no requirement of an external control. So they will just go on running without any intervention. So now we can look at the quantum version of that, a quantum absorption refrigerator. And some of the early work was done by, for example, Ronnie Koslov, who's in the audience. The idea goes around with having 3 baths here. In this particular setting, there are 3 systems, 3 quantum systems. So the purpose is to cool this object and draw heat from a cool bath from here, the reservoir to be cooled, which is driven, the cooling is done on this bath, and in order to drive this cooling process, we extract heat from this bath over here. So this heat is basically providing the free energy to drive this refrigeration process. And some of the early proposal to do this with superconducting circuit was done by Patrick Hofer back in 2016. And there was in fact a proof of principle realization with atomic systems back in 2019. However, it's not really obvious how you would utilize this in a practical setting. And this is where our experiment comes in, where we use this for a qubit reset. So the way we do a qubit reset with quantum absorption refrigerator would be to use these 3 quantum objects, which happen to be qubits. These two qubits with their baths form the actual quantum thermal machine, which is going to cool this third target qubit over here. So these are the two qubits which they have engineered couplings to control reservoirs, whereas the target qubit could be coupled to an uncontrolled reservoir, to the environment, for example, with undesired coupling. And that is why we want to try to cool that. Passive thermalization would mean that the time scale of cooling of this is about T1 given by 1 by gamma, where gamma is the coupling with the uncontrolled reservoir. And the residual population is again given by the temperature of this uncontrolled reservoir. So this is what we try to cool. And the process that would work over here is in this setting when the target qubit is excited, this is what we want to basically reset to the ground state. This wouldn't work when the other two qubits are not excited. But on the other hand, when this hot qubit, the red one, is excited, then we have this resonant, and in the presence of this resonance condition, which satisfies the basically energy conservation when you have this process, and it activates this Hamiltonian. These two excitations are exchanged with the middle qubit, which finally excites the middle qubit, and that is then released into the bath, its own bath. And in that way, we basically achieve the reset of the green qubit. So in order to build this machine, we need two key ingredients. So that is the control baths that we should be able to control, and a three-body interaction, which is connecting all these three qubits. So to have control baths, we use microwave waveguides as the heat baths. Here, for example, a waveguide is coupled to a qubit, and what we do is to apply a noise source at room temperature, which we can synthesize and control the magnitude, which is sent through an attenuator, which attenuates to the right magnitude, and then it is used to populate the waveguides with that noise. So that usually is a narrow bandwidth noise, but the main point is that it covers the transition of the qubit where it will interact with the qubit. So we can engineer this with our room temperature electronics, and this can have ohmic spectral density. We can synthesize the spectral occupation, and we can also analyze any scatter radiation later on. This is something which formed a previous work from our group, where we showed that the qubit can be used as a primary thermometer for this synthesized radiation, which we call quasi-thermal, because it's not really full broadband as you would get from a black body radiation, but it's actually synthesized over a narrow range of frequency. And we could see a very good agreement between the synthesized and the physical temperature, so it's something we can control quite well. Now we come to the quantum absorption refrigerator. So this is the scheme. Over here we have three qubits, where the two of these are connected to this to microwave waveguides, and the target qubit, which is what we want to cool, is connected to a resonator which will be used for the readout. So here we have engineered the three-body interaction such that a single excitation in the red qubit and the green qubit leads to a double excitation in the blue qubit, where we go to second excited state when there's a decay of this single excitation on both the qubits. And the way we achieve this is by using Josephson junction, which enables four-wave mixing. Josephson junction have this cosine function, which basically mix these modes in a manner which leads to this kind of terms when we satisfy the resonance condition, that is omega 1 plus omega 3 is equal to 2 omega 2 plus alpha 2, where alpha 2 is the anharmonicity of this transmon qubit. So these are realized with aluminum-based transmons. We operate them in a dilution refrigerator, and one of those qubit, the blue one over here, is frequency tunable. It's frequency tunable because we want to be able to control the resonance condition so that we can satisfy that. These are the range of the frequencies. So it's a standard range between 4 to 8 gigahertz, and the qubit that we usually use for quantum computing is also around 4 gigahertz. So that's the typical qubit that we are trying to cool in our experiment. We realize the physical thermal baths now for all these two different qubits, the red and the blue one. So in order to do that, we basically want to populate the waveguides with the right number of thermal photons. So we basically, which relates to the temperature of that bath via the Bose-Einstein equation. And what we basically do at room temperature is synthesize power spectral density, which is proportional to that number of photons. So this is what we send at exactly the frequency of the qubit transitions, where we want to have those thermal baths. So ultimately, in this case, for the qubits that we have, so qubit 1 and qubit 2, we basically make sure that our thermal our radiation, the synthesized radiation, covers those transitions in this frequency layout. So now, what I would like to show is that our three-body interaction, which I suggested earlier, we use Josephson junction to engineer, works. So in order to do that, we have this particular pulse scheme, where we excite the qubit 3, which will try to reset, and then we resonantly drive the qubit 1, and we measure whether that resets the qubit 3. This will only happen in the condition when we satisfy the resonance condition. So this is the experimental plot, where on the bottom axis, we are sweeping the drive frequency on the qubit 1. On the vertical axis, we are sweeping the qubit 2 frequency with the flux line so that we can satisfy the resonance condition. And when these two frequencies match up at over here, we see that the state of the qubit 3, the third qubit, drops rapidly. This is how we show three-body interaction, where we see two of these qubit characteristics, and we see an effect in the third qubit. Now, if we go to that resonance condition and look at actually the state of the qubit as a function of the duration of our resonant drive, so that during this time we are basically sucking out the excitation from the qubit 3, we can see that with sufficient resonant drive, we can reset the qubit 3 with a coherent drive. So far we were applying a coherent drive in the qubit 1. But now, to operate this like a quantum absorption refrigerator, we will now apply thermal baths on the qubit 1 instead of the thermal drive, instead of the coherent drive. So the steps are pretty much similar. We excite the qubit 3, then we elevate the temperature of the hot bath, the qubit 1, and then we measure the population of the qubit 3 with this scheme over here. So this is the experimental result. In the beginning, when we apply almost zero number of hot photons in the wave in the qubit 1, the qubit 3 is decaying at its characteristic time scale, which is about 17 microseconds. This is the standard time scale for the energy relaxation rate of a transmon qubit. But as we increase the number of photons in the hot bath, over here with this different legends, we begin to relax the qubit 3 much faster. In fact, by the time we are applying a lot of photons in the hot bath in the qubit 1, the qubit 3 has dropped by a factor, the relaxation time of the qubit 3 has dropped by a factor of about 70 just by heating the qubit 1 with the hot bath. So what is interesting to see is what is the population of the qubit 3 as we keep on increasing this. So this actually goes below these two dashed and dot lines. So what are these dashed lines? The green one is the passive thermalization of the qubit bath to itself, the target qubit to its own bath, which is about 0.028. And if we were to hypothetically connect this target qubit to the coldest bath available, which is given by this blue line, it would have reached that population. But we are actually cooling down the target qubit to a population much below this line. So in fact, we are going to a steady state population about 0.0005. With where we have already hit the noise floor of our measurement. And from here, we can check what is the qubit temperature, and it turns out to be about 23.5 millikelvin. This is actually colder than the coldest bath available, which was the bath of the the QT qubit, which is 45 millikelvin. So we actually cool the qubit to a temperature much lower than what is available in the circuit. The reset time is about 1.6 microseconds, so this is not very impressive when we look at other protocols, but the population we have reached is actually quite competitive to the other studies. So here, for example, we are comparing to the state of the art. So some of the state of the art is of the order of some hundreds of nanoseconds with a population around 0.1%, and our refrigeration basically brings it down to a very similar level, or even lower if we allow it a long enough reset time on the x-axis. So in summary, what we have demonstrated over here is a useful, fully autonomous quantum thermal machine with this, because it cools the qubit autonomously without any coherent drive. All we need is to apply the thermal baths to the hot qubit and the cold qubit. This is, the performance is competitive with the state of the art. And it's quite a resource efficient approach to quantum computing tasks because you're using thermal baths which could be abundantly available. So one outlook could be, for example, this chips are studied in dilution refrigerator. So they are put somewhere over here at the bottom, which is at about 9 millikelvin. But this refrigerator also offers a few other temperature stages at about 100 millikelvin, 70 millikelvin, and 3 Kelvin. And these are they are already abundantly available. So we could actually make circuit connections where we connect this hot bath, the hot waveguide to, for example, 3 Kelvin, and the cold bath already to 10 millikelvin, and that by itself will drive the refrigeration. It will keep on cooling down the target qubit to the temperature, to the level that I showed earlier in the previous slide. So what more we could say about this is that this is a very interesting platform to use circuit QED with thermal waveguides for studies in quantum thermodynamics. Thank you.
Very beautiful experiment. I guess one question is, if you don't use thermal resources, if you use coherent resources, can you also cool the qubit? Can you cool it more than just with thermal resources, or are thermal resources the best you can do?
No, actually, it turns out that coherent drive is more efficient if you want to reset. So you see the reset time is actually lesser than we use the thermal radiation. And part of the reason is that in a coherent drive, you make sure that the qubit 1 is excited, is in a pure state, basically, excited. On the other hand, when we use thermal baths, it's actually in a mixed state of excited and ground state. So thermal bath does not do as good as a coherent drive. On the other hand, it allows you to drive it autonomously without the use of coherent drive.
Yeah, thanks. Very nice experiment. So I was wondering about the spectrum of the noise on qubit 1. So do you take care of avoiding the 1 to 2 transition of the qubit, or is the noise spectral density also covering this?
Yeah. So in this case, we made sure. So the qubit 1, we want to only excite the first excited state. On the other hand, in the qubit 2, we basically wanted to make sure that because both the first excited state and the second excited state are involved in the process, we want to apply a thermal radiation to both. However, in the experimental plot that I showed you, we actually didn't apply any synthesized noise because we wanted it to be as cold as possible. But we have done other experiments where we increase the temperature of the cold bath to see how does the population change. And in that case, we would change the thermal radiation for both the transitions.
Okay. So if you were to use the 3K stage to warm up qubit 1, I guess you would need filters on the way so that only the noise at 0.1 reaches qubit 1, right?
You mean when we use a natural source instead of synthesized? You're right. You need to use a filter for that.